Hello. In this video, we're going to talk about principal components. And this is something that shows up in statistics. And the theory behind principal components is based on quadratic forms and the spectral theorem, which is something we've been talking about in previous videos. So the purpose of this video is to explain what principal components are and how they help us to understand data using a simple example. And I also want to explain how principal components are related to linear algebra. To do that, let's review what we learned before. This is when we had a quadratic form in two variables. Any quadratic form in two variables has the form ax1 squared plus bx1 x2 plus cx2 squared. And this is the same as what you get by taking the row vector x1, x2, multiplying it by the matrix A, B over 2, B over 2, C, and then multiplying it by the column vector x1, x2. And this matrix is a symmetric matrix, which we called A. And I'm assuming that A, B, and C are real numbers, so this is a symmetric matrix with real entries. And by the spectral theorem, A has a decomposition, Q, which has columns which we'll call U1 and U2. That's Q, lambda, which is a diagonal matrix, and Q transpose, or Q inverse. They're the same. Q transpose equals Q inverse because Q is an orthogonal matrix. So U1 and U2, in this case, are orthonormal eigenvectors of A with eigenvalues lambda 1 and lambda 2. And here I'm arranging lambda 1 and lambda 2 so that lambda 1 is greater than or equal to lambda 2. And the relevance of this is that when we look at the associated quadratic form, which we'll call this z of x comma y, or z of x1, x2, since I'm using x1 and x2. This is a function of two variables, x1 and x2. But if you look at what happens when you only consider the values of the quadratic form on the unit circle, so that's the unit circle. Here's the x1 axis and x2 axis. So this is the domain of the quadratic form z of x1, x2. And if you only look at the values of this quadratic form on this blue circle, then it turns out that it has the largest value, and the largest value is lambda 1. So let's say, I don't know, let's say it's here, lambda 1. And this is obtained when you plug in u1, the vector u1, into z. Okay? And the quadratic form attains a minimum value of lambda 2 at u2. So if you imagine two axes like this, and these are perpendicular to each other. So if you think of new axes like this, the u1 axis and u2 axis, when you plug in the value which is u1 equals 1, u2 equals 0, you get lambda 1, the value lambda 1, and that's the largest value of the quadratic form on the unit circle. Okay, and then lambda 2 is the least value of z on the unit circle. And that's one way to interpret the eigenvalues and eigenvectors of this 2x2 symmetric matrix, A. So we're used to thinking of eigenvectors as vectors that get stretched by A, and lambda, the eigenvalue, is a scaling factor. But now we're thinking of eigenvalues and eigenvectors in a different way. If you have a 2x2 symmetric matrix, then the eigenvalues tell you the largest and smallest values of the quadratic form on the unit circle, and the u1 and u2, the eigenvectors, tell you where those eigenvalues occur. And we're going to apply this fact to a statistics example. And so let's say that you have some data. Okay, let's say that you're measuring some quantity and you have a sample of 6, say, people, person 1, person 2, person 3, person 4, person 5, and person 6. And you measure 2 quantities. So let's say quantity 1 of each person, and you measure quantity 2. And let's say that quantity 1 has these values. So we make this table and specify quantity 1 and quantity 2 of your six people. Right. And what we're looking for is we're trying to get a sense of the variation or the variance in the data. Okay. So this is like a matrix. This is like an observation matrix, a matrix of observations. Which is A, which is like this. Okay. So this matrix has 2 rows, right? Row 1 and row 2, and each row corresponds to the quantity or feature, some sort of aspect that you're measuring. Okay. Now if you have n, so here I have a sample of n equals 6 people, and if we let m be the average, m is the mean, of n measurements, say t1 to tn, then we say that the sample variance of the vector t1 through tn is 1 over n minus 1 times the sum from I equals n of ti minus m squared. Okay. So in this case, if you look at row 1, so in this case, n is 6, so n minus 1 is 5. And my TIs are these numbers here. So if I look at the sum, well, first let's find the mean, m. That's 1 over 6 times 19 plus 22 plus 6 plus 3 plus 2 plus 20. That's equal to, let's see, 41, 47, 50, 72 over 6 is 12. So the mean is 12. And what I can do is I can think of the sample variance as 1 over n minus 1 times the dot product of the vector t1 minus m, tn minus m with itself. So what I should do is I should subtract the mean from each row. So I'm going to find the sample variance of each of these two rows. In row 2, again I have n equals 6, and my mean is 1 over 6 times this sum, 12 plus 6 plus 9 plus 15 plus 13 plus 5 equals 60 over 6 is 10. So I should subtract 12 and 10 from each row. And when I do that, I get this vector, I get these two vectors, which I'll call the matrix B. So I subtract 12 and 10 from each row, and when I subtract 12 and 10 from the corresponding rows, I'm going to get this matrix 7, 10, negative 6, negative 9, negative 10, 8, 2, negative 4, negative 1, 5, 3, negative 5. And I define the sample variance, so now I can find the variance, the sample variance of each row. But actually, the sample variance is an example of something called the sample covariance. So let's say I have two vectors both with mean 0. Okay. And let's say that these are in Rn. The sample covariance, and so what I do is I'm assuming that my u and v have mean 0. So that means that if I add the components, I get 0. The sample covariance of u and v in Rn, if u and v have mean 0, is defined to be 1 over n minus 1 times u dot v. So now I have these two vectors which I can think of as u and v. This first row is u, and that second row is like my v. And notice this is a special case of what we had before, because when you take your vector t1 through tn and you subtract the mean from each component, you now get this vector which has mean 0, right? This vector has mean 0. So the sample variance of the vector u, and u is in Rn, if u is in Rn and has mean 0, is just the covariance. So let's just call this the covariance of u and v. So this would be the covariance of u with u. It's 1 over n minus 1 times u dot u. And so what you can do is you can form something called the sample covariance matrix. And that's what you get by the matrix S, where the ijth component is the covariance of the vector ui and uj. Okay. Well, that can be found by doing this with your matrix B. If I have this matrix B, what I can do is I can take 1 over n minus 1 times B transpose. And let's see why this is true. So in this case, this example, S is 1 over 5 times B. B is this matrix. Times B transpose. And the reason is because if I look at the 1, 1 entry, I get the 1, 1 entry by taking this first row and taking the dot product with this first column. That's just the dot product. And if I take the 1, 2 entry, that's found by taking this vector and multiplying it by that vector. Well, that's just the dot product of these two vectors. So when I do that, I get this matrix, which is 86, negative 27, negative 27, 16. Now notice, this is a symmetric matrix. This is a symmetric matrix. And in general, this is going to be a symmetric matrix. So let's just review what we did. We started out with this matrix of observations A. Okay. Then you subtract the mean of each row from each row, and that gives you B. So what you do to get B is you subtract the mean from each row of A. Each row has a different mean. Okay, and so you subtract the mean, that mean from each row, and then that gives you this matrix B. And we get the sample covariance matrix S by taking 1 over n minus 1 BB transpose. And this is a symmetric matrix. As you can check, the transpose of S is itself. Okay. So this matrix tells you the covariance of the vector ui with the vector uj. And if you think of those as measuring the quantities, right, it measures the covariance of quantity I and quantity j. Now let's think about how we can bring in the spectral theorem into this context of the data. So if we look at the variance, let's say that we have the variance of u1 and the variance of u2, what happens if we take the variance, the sample variance of a linear combination? So let's call, okay, I call these u1 and I call these vectors u and v. So let's say that I had the sample variance of cu plus dv. Well, the sample variance of cu plus dv, okay, where c and d are constants, cu plus dv is what I get when I let's see. Well, the sample variance of cu plus dv, does cu plus dv have mean 0? Yes, because u and v has mean 0, right? So the sample variance of this linear combination is just the dot product with itself. Okay. I guess divided by n minus 1. This 1 over n minus 1 is something like a normalization factor. Okay, it's not super important for what we're talking about. Now let's say we take the vector CD like this, and we take the matrix whose rows are u and v. Well, this is actually going to be the row vector cu plus dv. So I get this. So here I'm thinking of these as rows, right? And so therefore the sample variance, okay, of cu plus dv, this matrix with rows u and v, that's B. And so this sample variance is the same as CD times B. Okay, this is a row vector. I need to take the, I need to multiply that by the corresponding column vector, and that's the transpose. So I need to multiply by B transpose times this column vector CD. And then I need to divide by 1 over, I have to multiply it by 1 over n minus 1. Okay. So I can find the sample variance of any linear combination by looking at this. But this is a quadratic form, right? If I replace C and D with x1 and x2, this is a quadratic form. This is a quadratic form. And so we can ask, which C and D, suppose we restrict the vector CD to be a unit vector. Now we can see what the largest and smallest sample variance is. Right? This value of the quadratic form is the sample variance, and we learned above that when you restrict the quadratic form to the unit circle, we have a quadratic form in two variables. When you restrict to the unit circle, the largest and smallest values, the greatest and least values are lambda 1 and lambda 2, and they occur at the unit eigenvectors of your matrix. And we're applying it to the sample covariance matrix. So we're applying the spectral theorem to S. So this quantity is equal to the sample variance of Cu plus dV. And so if we restrict CD to be a unit vector, then by what we've seen, okay, the largest sample variance, if you restrict CD to be a unit vector, is lambda 1 and this occurs at U1, and the least sample variance is lambda 2 occurring at U2. And this is where we write S as Q lambda Q transpose, where lambda 1 is greater than or equal to lambda 2. Okay. This is the largest possible sample variance, and the least possible sample variance is lambda 1 and lambda 2 occurring at the unit eigenvectors. This is the largest, smallest sample variance of all the possible sample variances, where you take linear combinations of the rows of B, and you take linear combinations so that the C and D, those coefficients, have unit length, right? The vector CD needs to be a unit vector. Okay? And so what that means is that the direction, so intuitively, the direction U1 captures the largest amount of variance in the data. Actually, what is the total amount of variance in the data? Well, the total variance, the total sample variance, is what you get by taking each feature and then adding up the variance in each feature. So in this case, since the diagonal entries tell you the variance in each feature, the sum of the diagonal entries is the total variance. So the sum of the diagonal entries of S is the total variance. Okay. And there's this fact, so there's this general fact that we can use, that if S is Q lambda Q inverse, okay, then the sum of the diagonal entries, that's called the trace of S is equal to the trace of lambda. Well, the trace of lambda is just going to be the sum of the eigenvalues of the matrix S. Okay? So that means that in this scenario, the total variance in the data is the sum of the diagonal entries. That's the sum of the eigenvalues. Well, okay, we have to find what the eigenvalues of this matrix S are. So if you perform the diagonalization, you end up getting that u1 is 0.95, negative 0.32. Okay, you could also multiply this by negative 1 and make the unit vector go the other way, it's fine. And lambda 1 is 95.2. And u2 is 0.32, 0.95. Of course, as we would expect, because these are orthogonal. And lambda 2 is 6.8. Okay, so that means that the total variance is 95.2 plus 6.8. That's equal to 102, which is what we would expect, because when you look at S, you get this matrix. If you sum these up, you get 102. That's the total variance in the data. Okay. But the eigenvalues are lambda 1 and lambda 2. And so what we can say is that in some sense, the direction u1 captures, okay, what fraction of the total variance? Well, the variance in the u1 direction is 95.2. So it captures 95.2 over 102, which is about 93.3% of the total variance. And then the direction u2 captures the remaining part. So about 6.7% of the total variance. Okay. Capturing the total variance is a kind of vague statement. It just means that if you take the variance in the u1 direction and then divide by the total variance, that's the percentage you get. So these eigenvectors are called the principal components of the data. So u1 is the first principal component and u2 is the second principal component. Yeah. So u1 is the first principal component. I'll call it PC1. And u2 is the second principal component, so that's PC2. So going back to our original data, if you center the data so that the mean is 0, the mean of each row is 0, then you have these data points, 7, 2, 10, 4, negative 6, negative 1, negative 9, 5, negative 10, 3, 8, negative 5. These are your 6 data points. If you plot them, then it turns out that if you take the u1 direction, which is 0.95, negative 0.32, that's something like this. Okay, this direction is going to capture most of the variance. And vaguely what that means is that if you could find one direction that captures most of the information, it would be this one direction. And then the second principal component is orthogonal to it, so it was 0.32, 0.95. That's something like this. So a unit vector in this direction would be the second principal component. Okay. So that's what principal components are. Let's just review what they are. you have your matrix of observations, and the way I'm organizing the matrix is I'm taking the people and putting the data as columns. Okay, maybe it's more typical to put the data as rows. In that case, you would have to take the transpose. But I'm organizing the data points as columns of this matrix of observations. And the quantities or features are going to be in the rows. And what you first do is you subtract the mean from each row, and so therefore now you get a matrix where the mean is 0, so the sum of the entries in each row is 0. You get that matrix B. You take this sample covariance matrix 1 over n minus 1 BB transpose. That's a matrix where the diagonal entries tell you the variance of each quantity, and the, in general, ij entry tells you the covariance of quantities ui and uj, quantities I and j. And then that's a symmetric matrix, and so that's going to have this decomposition q lambda q inverse, and the unit eigenvectors, those are the columns of q, those are called the principal components of the data. And the first principal component, that corresponds to the largest eigenvalue, tells you the direction in which you're going to capture most of the variance in the data. And if you think of the variance as an amount of information, it tells you the most amount of information. So if you have these data points, which you can think of as in R2, and you somehow want to only take one direction, like one line that captures as much as possible, it would be this vector. And we actually see how much variance is explained. The variance explained by the principal component u1, the first principal component, is lambda 1, the largest eigenvalue. And then in this case, you only have two principal components. And then the second principal component tells you the least amount of variance that's captured by the vector u2. It's orthogonal to u1. Okay? And we'll see what happens in a future video when we look at more features, right? More quantities. Then you're going to have more than two eigenvalues. But in the case when you have two eigenvalues, this covariance matrix is 2 by 2 matrix, then it's fairly easy to understand what's going on. And again, the point is that this is how we're applying this fact about the quadratic forms, the constrained optimization. The point is that the variance, when you take a linear combination of the rows, okay, you take a linear combination of the features, but you take the coefficients such that that vector has unit length, okay, then what you're really doing is you're restricting this quadratic form, which is the variance. The variance is the quadratic form. You're restricting the variance to the unit circle. And now we're applying this fact about quadratic forms and this interpretation of the eigenvalues and eigenvectors of a quadratic form when restricted to the unit circle. So this is the case when, again, you have a 2 by 2 matrix, a quadratic form in two variables, and we'll see in a future video what happens when you have more variables. Okay. So I hope that you now have a better understanding of what principal components are and how they're related to quadratic forms and the spectral theorem. Thanks.